I would like to start my presentation entitled Magnetic Resonance Image Reconstruction using Inception-based Convolutional Neural Network. So for the outline, first of all, I will talk about magnetic resonance imaging, or simply MRI, and then what is MRI scan acceleration, and then I will talk about U-Net. Because we are integrating Inception module with U-Net, I will discuss about both networks, and then we will discuss about our methodology, and then we will compare our metrics and images in results section, and at the end we will have our conclusion. So what is magnetic resonance imaging? What is MRI, and how does it work? So MRI is one of the most fascinating diagnostic procedure, which uses a powerful magnet and radio frequency to scan the objects. And MRI stores a data in frequency domain. I will talk about what is frequency domain and image domain later. And then MRI generates images with a transformation function, but there is a challenge in MRI, which is the long scan time, and the long scan time leads to patient discomfort, and then reduces image quality due to motion artifacts, because it's so hard for patients to stay for a long time during MRI, and then for sure increases the cost of the MRI scan. So first of all, it's important to know about K-space and then continue. So why we need to know about the K-space? Because MRI produces images in K-space, or we can say in frequency domain. As you can see here, these two images are the same image, but the left one is in K-space or frequency domain, and the right one is in image domain. But we can simply convert these two images together by for example, you can convert images in image domain by Fourier transform to images in frequency domain or K-space, and vice versa. So here I would like to talk about the reason for long scan time in MRI. So MRI scanners acquire collections of signals in frequency domain. There are different techniques that the MRI can collect data, but we use Cartesian, as you can see in the right image. The Cartesian technique fills the K-space row by row, and the line are acquired with a constant rate. As we know, MRI produces high-resolution images, and high-resolution images needs more pixels, and more pixels leads to more measurement, and also again leads to more steps through K-space, so that at the end leads to longer scan time. So there is a solution for that we can speed up the process of MRI. So by doing undersampling, decreasing the amount of data acquired. So what does that mean? It means that we can skip some lines in data acquisition, as you can see in the right here, that we are skipping some lines in between, but this undersampling, doesn't meet the sampling theorem, which we call Nyquist theorem. So Nyquist theorem is saying that sampling frequency should be at least twice the highest frequency, but as we are skipping some lines, so it means that we are losing our data, we are losing some important information. So this is why undersampling cannot meet the sampling theorem. So as you can see here, undersampling, the right one is undersampled images, the left image is showing the original or fully sampled image. And as you can see, the undersampled image is corrupted and it's blurred. So we need to find a solution for that. Before going forward, it's important to know about the differences between low frequency and high frequency. So if you look at the top images, as we discussed about that in the first slides, this one is showing original images. The left image is showing in K-space, and the right image is showing the image in the image domain. And then if you look at this one, we would like to talk about low frequency components. So for low frequency components, which we need to keep data that are in the center of the K-space. So the center of the K-space has more energy and information about the image, and more information, it means that information about contrast, about brightness, and general shapes. As you can see the image in here, you can see everything about the contrast, brightness, and general shapes. And also, if you take a look at the bottom one, you can see that we are just keeping the periphery of the image, and we are skipping the middle or center of the K-space, which we can say that they have high frequency components in periphery. And the periphery of the K-space give us information about edges, as you can see, and details. So here is the general strategy of the undersampled MRI reconstruction problem. So basically, if you first take a look at the top one, this is the procedure that MRI usually do. MRI produces images in K-space, and easily with inverse Fourier transformer, we can convert those images in image domain. But in this study, we want to speed up the process, and then we need to do reconstruction and reconstruct our images. So this is why we have this procedure that we first do subsampling and produce undersampled K-space data. And again, we wanted to convert images in frequency domain to image domain. So as we said, with inverse Fourier transform, we can convert images in K-space to image domain, but this image is corrupted. So we need to do reconstruction. So this is the part that we introduce our architecture. I will discuss about our architecture in the next slides. And then by reconstruction, we can convert our corrupted images to reconstructed images. So let's see what is the U-Net. So deep learning is one of the methods of reconstruction that I can say U-Net is one of the most popular deep learning method. So as you can see, U-Net has the U shape. So we have encoding section and we have decoding section. So encoding section is related to the downsampling part, and decoding is related to upsampling part. So as we discussed about that, the input images is our corrupted images and our output should be our reconstructed images. So the size of the image is 256 by 256, and then we applied 3x3 convolution, batch normalization, and Rayleigh activation function. And then we will have our max pool 2x2, which half the size of the image to 128 by 128, and it continues up here. And then we have our upsample 2x2, which double the size of the image, because we need the size of the output image to be the same as the size of the input image. So this is why we again do upsampling to have the size of the image be the same as the input image. And then in between we have concatenation. So by concatenation we are able to pass all the information, all the features from the previous block to the next block. So concatenation prevents information loss and overfitting. This is why we do concatenation in between. And then again, it continues up here, and then we can have our reconstructed images. So this is the whole procedure of the U-Net. So, but in this study, we integrated U-Net with Inception module. So let's see what is Inception module. So Inception module for the first time proposed by researchers at Google. And the idea behind of the Inception module is to make the architecture wider instead of deeper. So we don't want to just add layers to make it deeper. So instead, we decided to make each layer wider and wider. So the reason for doing this is because it prevents complexity. Because complexity causes overfitting. So we decided to integrate an Inception module to prevent the complexity, and also Inception module extracts more information from the image. So if you take a look at this part, you can realize that in Inception module, we can have the different combination of convolutions and max pooling. So you can have 1x1 convolution layer and combine it with 3x3 and 5x5, and then you can combine it with 3x3 max pooling, and then you can concatenate those layers and pass it to the next layer. You can do concatenation or you can do summation. So here is the architecture of the proposed model. So this is exactly the same as the U-Net, but the difference is that we combined 3x3 convolution with 5x5 convolution in this part, and do summation and pass it to the next layer. And then we repeated this one in the last layer as well. As you can see, we combine 3x3 convolution with 5x5 convolution, and again did summation and pass it to the next layer. So in the future, for our future work, we decided to continue this and combine more convolution layers, and maybe we can even do this procedure in other layers as well. So for example, we can add it here, and depends, we need to implement that. So for data set we use fast MRI. There are different kinds of data sets in fast MRI, but in this study we use T2 images, and it has 2,250 axial T2 images. In this study we use this, and also I can say that 70% of the data set is dedicated to training, 10% is dedicated to validation, and 15% dedicated to testing. So for evaluation, we use this, 4 metrics: mean square error, or MSE, and normalized mean square error, or NMSE, which measure the errors. So it is clear that the error, we need a lower value. So the lower the value, the better the result and better the quality of the image. And also the third one is a structural similarity index measure, or SSIM, which measures image similarities in terms of brightness, structure, and contrast. So in this case, for these metric, the higher the value, the better and more similarity between the reconstructed image and the original image. And the last metric is peak signal to noise ratio, which we call PSNR, which measures the intensity of the image. Again, for PSNR, the higher the value, the better the quality of the image. So here we want to compare learning curves comparing learning curves of U-Net with proposed model. So, but we use just low frequency of 8%. So the x-axis shows the number of iterations, and y-axis shows loss. The orange line is showing validation, and the blue line is showing training. So in U-Net, the validation loss is higher than the training loss in higher iterations. As you can see in this section, you can see a little bit of fluctuation here, which we can conclude that the model is slightly leaning toward overfitting. But in proposed model, if you look at, especially we are comparing in the higher iterations, because everything is fine in lower iterations. So here the proposed model was able to extract more information from the image, and the model performs well in validation data as well as training data. So it shows that the reconstructed images is more, has better quality, and the similarity is more with the original image. So if we want to compare images, we are comparing again U-Net in low frequency of 8% with proposed model, again in the same low frequency. You can see for example, this part is showing, the large red boxes is showing the enlarged view of the small red boxes. So it is clear that in the proposed model, the features are pretty much the same as the features in Grand Truth image, which is our original image, the same in the below images. And you can see that the features is pretty much the same than the U-Net model. And also, if you look at the errors, you can realize that, so this is the error of the proposed model is less than the error in U-Net, the same in this picture. And if you take a look at the image in detail, you can find so many of these things that you can easily understand the proposed model is performing better. So here you can see the quantitative comparison, and again we compare U-Net with proposed model in these 4 metrics. And but in this table we also provided some information, and we implemented in low frequency 20% as well. For MSE or an NMSE, as we said, that the lower the value, the better the quality of the image. So you can easily realize that the value is lower in proposed model in both frequencies, 8% and 20%. And also SSIM, which shows similarities. We said that the higher the value, the better the quality of the image, and the similarity is more. So you can see that the values are higher. And again, in PSNR, the higher the value, the better the quality and intensity. So for a conclusion, I can say that if we want to compare, again, proposed model with standard U-Net, we can say that we were able to speed up the process by 3.2 times, and this integration integrating Inception module with U-Net network prevents overfitting, and the values of MSC and NMSC are decreased by 6.7%. And the value of SSIM is increased by 0.6%, and the value of PSNR is increased by 1.05%. So we can conclude that the proposed model eliminates more folding artifacts, and which leads to better visualized images and leads to better reconstructed images. So I would like to thank, first of all, my supervisor, Dr. Amirali Baniasadi, and also Dr. Vafay Eslahi for her guidance and support throughout the project. Here is my references of this presentation. Thank you so much. If you have any question, I will be happy to answer.